Surface integrals. We're going to start with a surface in three-dimensional space. And let's assume that we have a function, f of x, y, z, which is continuous and defined on this surface. We chop up the surface into patches, and we choose a point in each of these patches. And then what we do is we evaluate the function at each of these points, and then multiply by delta sk, which is the area of the patch that the point appears in. For each of these patches, we get this product, f of ck, dk, ek times delta sk. We add all those up, and then we take the limit of this procedure as n goes to infinity, where n is the number of patches. We call this the surface integral over S of f of x, y, z ds. And you could see the notation for the surface integral used here. In practice, to compute a surface integral, we can change it to a double integral by first parametrizing the surface, where the vector valued function used in the parametrization has components x of uv, y of uv, z of uv. And then we replace x, y, and z by what they are in terms of u and v. So we have f of x of uv, y of uv, z of uv, and we multiply by the length of the cross product of the partial derivatives of the vector valued function r with respect to u and v. And we've now changed the surface integral into a double integral over the region r dA. We'll see shortly how to do this in detail with some examples. It's worth mentioning that if no function appears inside of the surface integral, or equivalently there's a 1 in there, then that surface integral actually gives us the surface area of the surface S. Note that although the surface integral has nothing inside of it, when you change it to a double integral, the double integral will have the length of the cross product of the partials inside. Let's try an example. For your convenience, I put the formula for changing a surface integral into a double integral in the right-hand corner there, as well as how to do a surface area in terms of a surface integral. Go ahead and pause the video, try this example yourself, and then resume the video to check your answer with mine. Find the surface area of the cone, x equals u, y equals u cosine v, z equals u sine v, where u is between 0 and 2, and v is between 0 and 2 pi. Okay, so let's start by taking the cross product of the partial derivatives, where r is the vector valued function with components x, y, and z. So inside this determinant, for the second row, we put the partial of r with respect to u. The partial of u with respect to u is 1. The partial of u cosine v with respect to u is cosine v. And the partial of u sine v with respect to u is sine v. For the third row there, we take the partial of r with respect to v. The partial of u with respect to v is just 0 because u is being treated as a constant with respect to v. The partial of u cosine v with respect to v is negative u sine v. And the partial of u sine v with respect to v is u cosine v. When we take this determinant for the I component, we get u cosine squared v minus u sine squared v, or equivalent u times cosine squared v plus sine squared v. Since cosine squared v plus sine squared v is 1, we just get u. For the j component, we get 0 minus u cosine v. And for the k component, we get minus u sine v minus 0, or just minus u sine v. Now let's take the length of this cross product. So we add up the squares of the components and take the square root. So we have under the square root u squared plus u squared cosine squared v plus u squared sine squared v. We could factor out a u squared from the second and third terms. And since cosine squared v plus sine squared v is 1, we get the square root of u squared plus u squared, which is the square root of 2u squared, which is root 2 times the absolute value of u. Now, we could have actually just wrote u there because we see that u is actually between 0 and 2. Since u will never be negative in this particular problem, the absolute value of u and u are the same thing. Okay, now we're ready to compute the surface area, which is the surface integral over S ds. Notice nothing is inside because we're computing a surface area. However, when we change to the double integral, inside appears the length of the cross product of the partials, which we just found to be root 2 absolute u, which, as we said, is just the same thing as root 2 times u, because u is only taking on values between 0 and 2, which are non-negative. This is a pretty straightforward integral. We could do it as a product of the dv integral and the du integral. The dv integral just gives 2 pi, and the u integral is just a power rule, so it's just u squared over 2 from 0 to 2. And of course, we're multiplying by the constant root 2. So when we plug the 2 into u squared over 2, we get 4 over 2, which is 2. Multiplying, we get 4 pi times root 2, or 4 root 2 pi. Let's do another example. This one is a surface integral that does not represent a surface area. Go ahead and pause the video, try this yourself, and then resume the video to check your answer with mine. Evaluate the surface integral over S, x squared ds over the sphere, x squared plus y squared plus z squared equals 1. We start by parametrizing the sphere. Let's do it in the usual way using spherical coordinates. Since this is the unit sphere, rho is equal to 1, so we get the parameterization r of phi theta equals sine phi cosine theta I plus sine phi sine theta j plus cosine phi k, where as usual, phi goes between 0 and pi, and theta goes between 0 and 2 pi. Let's now take the cross product of the partials of the vector valued function. Inside the determinant for the second row, we take the partial derivatives of the components with respect to phi. We get cosine phi cosine theta, cosine phi sine theta, and negative sine phi. And for the third row, we take the partial derivative of each of the components with respect to theta. We get negative sine phi sine theta, sine phi cosine theta, and 0 since the k component has no thetas in it. Okay, now the I component is 0 minus minus, or just plus, sine squared phi cosine theta. For the j component, we get a minus minus, so just plus sine squared phi sine theta. For the k component, we get cosine phi cosine squared theta minus minus, or plus cosine phi sine squared theta. We could factor out the cosine phi sine phi from both terms, and we're left with cosine squared theta plus sine squared theta, which is just 1. So that gives us cosine phi sine phi, which is our k component. We now take the length of this cross product. So we square each component, add them all up, and take the square root. So we get under the square root sine to the 4th phi cosine squared theta plus sine to the 4th phi sine squared theta plus cosine squared phi sine squared phi. Using the Pythagorean identity, we see that the first two terms simplify to sine 4th phi, because we could factor out the sine 4th phi and we're left with cosine squared theta plus sine squared theta, which is just 1. And once again, now we could factor out sine squared phi from both terms, and we're left with sine squared phi plus cosine squared phi, which is just 1. So we get the square root of sine squared phi, which is just sine phi. Since phi is running between 0 and pi, meaning the angle is in either the first or second quadrant, and the sine of a first or second quadrant angle is non-negative, the square root just cancels the square. We do not need to worry about absolute values here. We're now ready to compute the surface integral. We're going to start by changing it to a double integral. First of all, we replace x by what it is in terms of the vector valued function. X is sine phi cosine theta, so x squared is sine phi cosine theta squared. And remember, we have to multiply by the length of the cross product of the partials, which we just found to be sine phi. Okay, now the region R is given by phi going from 0 to pi and theta going from 0 to 2 pi. So if we do it as d phi d theta, then the outer limits are 0 and 2 pi, and the inner limits are 0 and pi. And just simplifying the integrand, we have sine squared phi times sine phi is sine cubed phi, and cosine theta squared is the same as cosine squared theta. Since the limits are all constant and the integrand is a product of a function of phi with a function of theta, we could split this up into the product of two separate integrals. The integral 0 to 2 pi cosine squared theta d theta times the integral from 0 to pi sine cubed phi d phi. Now, for the first integral, we're going to use the power reducing formula. Cosine squared theta is 1/2 times 1 plus cosine 2 theta. And for the second integral, we're going to have to do a substitution, but let's first split sine cubed phi into sine squared phi times sine phi. The first integral is straightforward. 1 integrates to theta, and cosine 2 theta, there's a little substitution there. U equals 2 theta, du is 2 d theta. So we get 1/2 sine 2 theta from 0 to 2 pi. For the second integral there, we're going to rewrite sine squared phi as 1 minus cosine squared phi in preparation for doing our substitution. We were able to do that by the main Pythagorean identity. Now, when we plug the 2 pi in for theta, we get 1/2 times 2 pi, which is just pi. Plugging in the 2 pi and the 0 to sine 2 theta just gives us 0, so that goes away. Now, when we integrate the second integral there, we're doing a simple substitution. If we let u equal cosine phi, then du is negative sine phi d phi. So that just becomes a power rule, minus cosine phi plus cosine cubed phi over 3 from 0 to pi. So when we plug in the pi, we get negative cosine pi plus cosine cubed pi over 3, which gives us 1 minus 1/3. And when we plug in the 0, we get negative 1 plus 1/3. 1 minus 1/3 is 2/3. Negative 1 plus 1/3 is negative 2/3, but we're distributing that minus sign to get plus 2/3. So we get 4 pi over 3. You may want to check those last few computations carefully yourself. There are a lot of minus signs that can get you in trouble if you are not careful. Okay, let's try another example. Once again, pause the video, try this yourself, then resume the video to check your answer with mine. Evaluate the surface integral z squared ds, where s is the part of the paraboloid, x equals y squared plus z squared, with x between 0 and 1. Okay, let's start by parametrizing this paraboloid. There are many different ways to parametrize it. Let me parametrize it by letting y equal u cosine v and z equal u sine v. And then since x is y squared plus z squared, it follows that x is u squared cosine squared v plus u squared sine squared v, which is u squared times cosine squared v plus sine squared v. So that's u squared times 1, which is just u squared. So that's where that u squared comes from for the x component. Now, in this case, since x is going between 0 and 1, and x is u squared, u is also going between 0 and 1, and v is going between 0 and 2 pi. Okay, let's start by taking the cross product of the partial derivatives. So for the second row of this determinant, we take the partial with respect to u, which is 2u cosine v sine v. And for the third row, we take the partial with respect to v, which is 0, negative u sine v, u cosine v. So the I component is u cosine squared v plus u sine squared v, which is just u. The j component is 0 minus 2u squared cosine v. And the k component is negative 2u squared sine v minus 0. Now we take the length of this cross product. So we square each component, add them up, and take the square root. So under the square root, we have u squared plus 4u to the fourth cosine squared v plus 4u to the fourth sine squared v. The second and third terms, we could factor out the 4u to the fourth, and we're left with cosine squared v plus sine squared v, which is 1. So we have the square root of u squared plus 4u to the fourth, factor out the u squared, and we're left with 1 plus 4u squared, all under the square root. So the u squared could come out of the square root as an absolute value of u. Once again, we could have just wrote that as u because I see here that u is between 0 and 1, and therefore is not going to take on any negative values. Let's go ahead and compute this surface integral. We're first going to change it to a double integral. We're going to replace z by what it is in terms of u and v, which is u sine v. So z squared is u squared sine squared v. And then we also have to multiply by the length of the cross product of the partials that we just found, which is absolute u, or just u, because as we said, u is between 0 and 1. And times square root of 1 plus 4u squared. So we had a u squared, we're multiplying by an extra u, that's where the u cubed comes from. Okay, let's put the limits on. The v limits are 0 to 2 pi, the u limits are 0 to 1. We could split this into a product of two separate integrals because the limits are all constant and the integrand is a product of two functions, a function of u and a function of v. The first integral, we're going to use a power reducing formula. And for the second integral, we're going to have to do a substitution. If we let t equal 1 plus 4u squared, then by solving for u squared, we see that 4u squared is t minus 1, or equivalently, u squared is 1/4 t minus 1. And also dt is 8u du. So as I said, for the first integral, we're going to use the power reducing formula. We change sine squared v to 1/2 1 minus cosine 2v. And for the second integral, we apply the substitution we just did. In place of 1 plus 4u squared, I put a t. That's where the root t comes from. In place of u squared, I put 1/4 t minus 1. That's where that 1/4 t minus 1 comes from. Now there's an extra u there, which we group with the du, and we also needed an 8 for dt. So we justify putting the 8 in by multiplying by 1/8 outside of the integral. That's where the 1/8 comes from. Okay, so integrating, we have 1/2 v minus 1/2 sine 2v. Notice a little substitution, u equals 2v, du is 2 dv, so we get 1/2 sine 2v instead of just sine 2v. Now 1/8 times 1/4 is 1/32, and t times root t is t to the 1 times t to the half, or t to the 3/2. When we integrate that, we get t to the 5/2 times 2/5. And similarly, we have minus 1 times root t, or minus t to the half. That becomes t to the 3/2 times 2/3. Okay, and that's all going from 0 to 1. So after plugging in the limits, we get pi times 1/32, 2/5 minus 2/3. You might want to check the last computation carefully yourself. Now, in the special case where our surface has the property that one of the variables is a function of the other two, we have another method that we could use for computing the surface integral, which I'm going to go over now. I'm just going to do the case where z is a function of x and y, but it's very similar if x is a function of y and z, or y is a function of x and z. Now, in this case, when z is a function of x and y, we've already seen that we could parametrize our surface by letting x and y just be the parameters. And to emphasize this, we'll set x equal to u and y equal to v, so that z is equal to g of uv. Notice all I did here was change the names of the letters. It wasn't absolutely necessary, but I'm just doing it so that it's clearer as I go through this procedure. So our vector valued function is r of uv is ui plus vj plus g of uvk. So when we take the cross product of the partials, inside of the determinant for the second row, we take the partial respect to u, which is 1, 0, g sub u. And for the third row, we take the partial respect to v, which is 0, 1, g sub v. So for the I component, we get 0 minus g sub u. For the j component, we get 0 minus g sub v. And for the k component, we just get 1. And g sub u is the same as z sub x, because g is z and u is x. And similarly, g sub v is the same as z sub y. So now when we take the length of this cross product, we take the squares of each of those components, z sub x squared, z sub y squared, 1 squared is 1, add them up and take the square root. We could also write that as the square root of the partial of z with respect to x squared plus the partial of z with respect to y squared plus 1. In this special case where z is a function of x and y, we could change our surface integral to a double integral by replacing z by g of xy in the function. And instead of multiplying by the cross product of the partial derivatives, we could just multiply by the square root of the partial z with respect to x squared plus the partial z with respect to y squared plus 1. This is faster if we have z as a function of x and y, because we don't actually have to parametrize the surface in this case. Notice that this square root expression here is just the gradient of f, where capital F of xyz is little g of xy minus z. Right? Or we could have written it as z minus g of xy. It's the same thing since we're squaring all the components. All right, let's try an example. So try to do an example using this new formula, which I have on the bottom right here for your convenience. Pause the video, try it yourself, and then resume the video to check your answer with mine. Evaluate the surface integral xz ds, where s is the part of the plane, x plus y plus z equals 1 in the first octant. Okay, let me start by drawing a picture of the plane in the first octant. We've done this many times, but basically I just plotted the three intercepts. If I set x and y equal to 0, z is 1. And similarly, I get x equal to 1 and y equals to 1 as the other two intercepts. The corresponding region is the region in the xy plane bounded by the x-axis, y-axis, and the line y equals 1 minus x. We could get that equation simply by setting z equal to 0 in the equation of the plane, or we could just copy that picture, drawing that line and doing it geometrically by using the y-intercept and the slope, however you want to do it. Okay, so now we're ready to turn the surface integral into a double integral. First of all, we have to replace z by what it is in terms of x and y. Well, z is 1 minus x minus y. And then we have to multiply by the length of the gradient. To get this gradient, we could either look at x plus y plus z equals 1, or z equals 1 minus x minus y, or we could bring everything over to one side of the equation. It doesn't matter. So for example, looking at x plus y plus z equals 1, the partial with respect to x is 1, square that we get 1. The partial with respect to y is 1, square that we get 1. The partial with respect to z is 1, square that we get 1. Okay, so square root of 1 plus 1 plus 1 is the square root of 3. We'll pull that out. We'll distribute the x through the 1 minus x minus y to get x minus x squared minus xy. And for the limits, we look at the region. We'll do it as a type 1 region. X is going from 0 to 1, and y is going from y equals 0 to y equals 1 minus x. All right, let's go ahead and integrate with respect to y. We get xy minus x squared y minus xy squared over 2, or 1 half xy squared, and that goes from 0 to 1 minus x. Plugging in the 0 doesn't get anything, so let's just plug in the 1 minus x. We get x times 1 minus x squared times 1 minus x minus 1 half x 1 minus x squared. Multiplying all that out gives us x minus x squared plus x cubed minus 1 half x plus x squared minus 1 half x cubed. Now we just have a definite integral with respect to x. Just combining like terms a bit here, we get 1 half x cubed minus x squared plus 1 half x. Applying some power rules, we get 1 half x to the 4th over 4, or 1/8 x to the 4th, minus x cubed over 3, or 1/3 x cubed, plus 1 half x squared over 2, or 1/4 x squared. Plug in the 0 and 1. When we plug in the 0, it just goes away. So let's just plug in the 1. We get 1/8 minus 1/3 plus 1/4. Simplifying this gives us root 3 over 24. Once again, you might want to do all these last few computations yourself. They're all very, very straightforward, a little tedious. So you might want to just check it carefully yourself to make sure you get the same answer. Let's do one more. Go ahead and try this example. Pause the video, do it yourself, then resume the video to check your answer with mine. Evaluate the surface integral over s y ds, where s is the surface, z equals x plus y squared for x between 0 and 1 and y between 0 and 2. So we're going to start by changing the surface integral into a double integral. We don't have to change the y there. There are no z's, so there's nothing to worry about there. But we do have to multiply by the length of the gradient. And the partial with respect to x is 1. 1 squared is 1. The partial with respect to y is 2y. Square that, we get 4y squared. And then always add that 1. Or we can think of it as the partial of that expression with respect to z is 1. Okay, so that simplifies to y times the square root of 4y squared plus 2. The limits are clear. X is going from 0 to 1 and y is going from 0 to 2. So we could split this up into a product of two integrals because the limits are all constant and we have a function of x times a function of y as the integrand. In fact, no x's appear at all. So we get the integral from 0 to 1 dx, integral from 0 to 2y square root of 4y squared plus 2 dy. In preparation for the substitution, I'll throw in an 8 and pull out a 1/8, right? Because if we let u equal 4y squared plus 2, then du is 8y dy. The first integral just gives us x from 0 to 1. For the second integral, we get 1/8 4y squared plus 2 to the 3/2 times 2/3. Plugging in the limits, we get 1 times 1/12, 18 to the 3/2 minus 2 to the 3/2, which gives us 1/12, 2 to the 3/2, 9 to the 3/2 minus 1, or 1/12, 2 root 2 times 27 minus 1, which is root 2 over 6 times 26, or 13 root 2 over 3.